And I'm a very privileged person because it's generally seldom to have a 45-minute introduction to a talk. So thank you, Piero, for this. So you will understand. Okay, sorry. Yes, I must be on the cross. Wow. I'm the kind of guy who likes, you know, just moving, walking when I'm teaching. So, wow, it will be hard. Okay, so basically there are, of course, slides that you will understand, you know, from first glance. So it will be easier for me to give you the message. So 2 reasons to investigate the Mediterranean water cycle. Piero always said that. So the water resource is a critical issue in this region with many droughts. Here, it's kind of complementary sketch of map of what was shown by Piero. It's the water resource exploitation index. So it goes from 0 to 100%. And this shows that in some regions of the Mediterranean, we reach more than 75% of renewable water resources exploited. So very few to use more. The demand in water has been multiplied by 2 since the 50s, and we have about 20 million inhabitants without access to drinkable water. And the second, that was probably less emphasized by Piero, is it's kind of, you know, dual problems with water cycles. So we have droughts on the one side, and we have heavy precipitation and floods on the other side. So this is events that are really located in some seasons. It goes from fall in this region to, let's say, winter, more to the east. And between the 90s, 1990 and 2006, we had more than 175 flood events with nearly 30 billion euros damages and more than 4,000 deaths. Generally, the heavy precipitation occur mainly on what we call the Latin arc, which goes typically from Spain to the Balkans or to the Hellenic Peninsula. These are the regions where the floods are more frequent. But it also occurs where we less expect them, especially in the southern shore of the Mediterranean. For example, here, this is the Algiers case in November 2001 with nearly 1,000 deaths during this event. So it occurs everywhere in the Mediterranean. And the final aspect that was also introduced by Piero is the climate change. Here, this is a map showing a regional climate change index. So it comes from 20 models from the last, the one that last IPCC exercise. So it comes from 20 models, 30 scenarios, and what must be understood in this map. So you see, it's the map of the world, and if we have a very large circle, then it means that there is a very strong regional response to climate change. Meaning that here, and you see that there are 2 regions here, Northeastern Europe and the Mediterranean. And for the Mediterranean, it corresponds to a very significant warming. So between, let's say, 1.5 to 6 in the end of this century degrees, and a decrease of the mean annual rainfall. So this was shown by Piero previously, but also an increase of rainfall variability. So we'll see what it means, but basically it shows that heavy precipitation will probably increase in the future. I like this map. So this was shown in the 4th assessment report of the IPCC. So this is a map that places, relocate, I would say, the major cities with respect to their climate in the future. So you see that, for example, at the end of this century, the climate of Paris will be that of, let's say, southern Spain. Marseille is not very far from Paris, which is different on this map in the present climate. So, of course, it's a nice way to show how climate change impacts the Mediterranean region. So, why is this presentation focused on extremes? Oh, it moves. Okay, let's start. I hope there is no animation here. So let's start with the distribution, so it's the probability that this temperature here, sorry, it's in Fahrenheit, so this temperature occurs. So let's consider a climate with a mean temperature of 50 degrees Fahrenheit. So 50 degrees Fahrenheit is about 10 degrees Celsius, and 10 degrees Fahrenheit standard deviation is, so the width of here is about 5 degrees Celsius. So let's consider this climate A, and we shift in climate from A to B. And so this is B this time, and this is the difference between those two probability density function. The difference is in blue here, but what is of interest here is the relative difference, okay? So you see that you can see that, for example, the biggest change expected in future climate are for extremes with here more than 200% change, relative change to the present for the extremes. This is true for temperature, but this is also true for precipitation, where we expect, so the thin solid line is the present climate, the thick solid line is the new climate, and you see that there is a decrease of probability for small precipitation, whereas there is an increase of probability for heavier precipitation. So on what we can, okay, so this is, of course, the physical motivation to look at extremes, but the other, of course, motivation to look at extreme is its impact. So it's, there again, goes in resonance with what Piero showed on vulnerability. So here, for example, so it's only for Europe, the cost of droughts and heat waves. So the droughts and heat waves affect the largest number of people, so 15% to 17% of the total, 15% of the EU area is affected by droughts, and 17% also suffered, of people suffered from the impact of droughts. One of the most severe events was in 2003 with more than 30,000 deaths in Europe caused by the heat wave. And over the last 3 years, above 100 billion euros were of cost for droughts and heat waves. And regarding floods, between 1998 and 2002, we suffered 100 major floods, especially in the region of Danube and Elbe. And in between 1998 and 2004, we had more than 700 deaths and a displacement of about 1 million euros, 1 million people, costing about 25 billion euros. So this is the distribution of disaster occurrence, so droughts and extreme temperature, which are of interest here, are shown in pink and yellow, and flood here in blue. This is for disaster occurrence, economic damages, and number of affected people. You see that floods is a major natural hazard in Europe, and whereas the droughts and extreme temperature is of very large importance in terms of affected people. So, what also makes the difference between Northern Europe and Southern Europe regarding floods? Here it's so it's a time series. So it's the flood of the Gardon d'Anduze watershed, so which is located in southern France near Montpellier. Here we have Marseille, and here we have Montpellier, for those who know a little bit the region. And this is the rainfall, okay, in millimeter, as a function of time. Here it's the hours of the day. And you see here the peak of rainfall. And this is the discharge, so the water flowing in the river. And you see that the flow peak occurs only 6 hours later than the rainfall peak. So this is very specific from the Mediterranean region, where we have small watershed, steep slopes, and so we call them flash floods. So we have very little time between the rainfall peak and the flow peak, which of course has strong consequences in terms of early warning system, which is totally different from Northern Europe, where we have much slower floods. So here, of course, it was in southern France, but we have this in the Balkans, in Croatia, in May 2014. Also in Montpellier, it was a very severe event in September 2014. Here it's only 2014 because these are the pictures, the slides that I show in 2014, you can guess. I was given a talk in one similar session in October 2014, so only 1 week after this event. So this was very... So how this event occurs? As was said by Piero, so we have humidity. And one specificity of the Mediterranean region is that it is surrounded by many, many mountains. Okay, so typically we're looking at this, the heavy precipitation that occur in this region. And so humidity is broad. Generally, you have a low, so a pressure low. So the wind is blowing in that direction. So it takes humidity from high levels, around 4 kilometers from the Atlantic. And then because of this cyclonic circulation, it brings water of the Mediterranean with very strong winds. So the very strong winds favor also evaporation of the Mediterranean Sea. So we have a strong load, a heavy load of humidity that is brought to the foothills of the Cevennes, the Alps. And so what happens there, so we have humidity, sorry, it's in French, but okay. Just listen, I would say. So the air is humid, is warm, it is so pushed towards the mountain ridges, and then the warm air is lifted up by the mountains. Of course, the temperature decreases until it reaches the condensation level, and then it forms water. Okay, the droplets become more and more larger and larger. Okay, they collide. So the small droplets collide, they become larger as a snowball, for example. And then when they are heavy enough, they start falling. And so we have precipitation. And why do these precipitation are intense? Because first, they are lifted at very high rate. And second, because the precipitation are blocked by the mountains. So of course, if this rainy system could move here, it would generate much less damages. But it remains because of the blocking by the mountains. So we have very strong precipitation, and of course, the terrain, the mountains, the presence of the mountains play a key role in generating this heavy precipitation. And since these mountains have many small watersheds, we also generate flash floods. And to show you, to illustrate the importance of the orography, so the mountains, the presence of the mountain, here I show you a numerical exercise. So it's numerical simulation, and what we will do, we will remove in the model either the Pyrenees, which are located here. So this is the control where we have all the mountains, which are shown here in gray. We have a typical 20 meters per second wind. Frankly, I don't remember what the red line is, but here you have the precipitation amount. The maximum is shown here. It's 423 millimeters in one day. And we will remove, the mountains. For example, here we'll remove the Massif Central, which is this huge but not very high mountain. And you see that we decrease the amount of precipitation by 2, approximately. Okay, you have a more elongated structure, less intense precipitation. If we remove the Pyrenees, you see that we do not modify at all the results. It's just because here in this condition, the Pyrenees do not play a role here. The cyclone is located over the Iberian Peninsula, and so the flow is coming from the south, and so here the Pyrenees almost do not affect here. You see the very low, very weak winds here. The main jet is located over the Mediterranean Sea, so the Pyrenees do not affect the system. And if we remove this time the Alps, here you see that there again we divide approximately by 2 the amount of precipitation. So this is to show that how much the blocking by the mountain affect the precipitation. Here so we start again with this control. We have all our mountains, but this time we decrease or we increase the intensity of the wind. So here we have a less, with respect to the control run, here we have a weaker wind, a weaker jet coming from over the Mediterranean Sea. Here we have a stronger one. So don't forget, if the stronger the wind, the more intense the evaporation. Okay, so here you load the air masses with less water in this situation that you would do in this situation. That's why here you increase, you multiply by 2 there the amount of precipitation. Okay, so this is a real key feature that is applicable in this region, but in most regions of the Mediterranean because we have mountains everywhere. The other point, and this is in kind of preparation to the discussion about climate change, is this Clausius-Clapeyron law. Okay, the Clausius-Clapeyron law is the one that you learned at school. It tells us that the water holding capacity of the atmosphere goes up at about 7% per degree Celsius increase in temperature. So air holds more water in the form of vapor at higher temperature. Okay, so that's why you have less clouds and less precipitation during summer, because it's much warmer than during winter, where you reach 100% relative humidity at in a much faster way. Okay, so and this is a key. Okay, observation showed that this is happening at the surface and in lower atmosphere. For example, over the ocean, we had an increase since the 90s of about 0.55 degrees Celsius, and we could see that there is an increase of 4% water vapor. Okay, if we plot, in fact, as a function of the sea surface temperature with the column water vapor, so these are satellite data, you see that this exponential shape here, which in fact corresponds exactly to the Clausius-Clapeyron law, which shows that the amount of humidity that the atmosphere can hold increases as the temperature increases. Okay, so this means that we have more moisture available for storms and an enhanced greenhouse effect, so which there again means that more intense precipitation can be expected in a warming climate. Okay, if it's warmer, we will be able to hold more water vapor in the atmosphere. So when we reach saturation level, condensation, then of course you have a bucket of water that falls down with more water in it. Okay, that's the principle with the hands. So let's look at what's happening over land. So this is just an example, and I will, okay. So from all these meteorological stations, from our National Weather Service, we plot as a function of temperature extreme precipitation. So here I will show the extremes. So you see that, as expected, as the temperature increases, here to about 15 to 17 degrees, we have an increase of precipitation. The precipitation extremes increase, so the amount of water that falls during extreme precipitation increases, and then it falls down. It falls down just because of aridity. We are in an arid environment. It was shown by Pierrot. So at certain level, the amount of water which is available from the soil is not sufficient enough to, let's say, feed extreme precipitation. So after a certain temperature, we reach the arid summer, and so there is lower precipitation efficiency. So this hook shape is very specific, well, not specific, but at least it characterizes the Mediterranean area. If you move to a more arid region, for example, to the east, you will see that this temperature break will go down and down and down. Okay, but basically this hook shape is valid all over the Mediterranean. It's just an example here. So we took this let's say, previous stations, at least a subset of them, the one that had the longest time series. And we plotted only the maximum per year, so it's the year maximum precipitation, so it's only the extremes. And for all the stations here that you see, and of course you have, as Piero said again, you have this variability year after year, you have some variability. But if you try to see, if you draw a line here showing that would show the trend, there is a significant trend. Okay, there were some here. You obtain a 4% increase per decade in heavy precipitation. It's not always as significant all over the Mediterranean. So I'm back to Piero. I agree with him that precipitation is a trickier problem. Okay, so when I'm questioned by journalists about, there is one big event in this region, so generally I know that journalists will contact me, and they, of course, have always the same question: is climate change responsible for that? So, of course, back again to what Piero said, we're not able to say, it was a fantastic introduction. So, of course, we cannot say, of course, yes, this one you can attribute to climate change. But what we can say is, here there is, from a large number of observation, so 51, I think it's in the middle of probably 10 years of observation. So there was a plot. From this observation, colleagues model with statistical distribution the relation between the precipitation and the return period. So for two data sets, one, let's say, in the present and one in the 50s. And they come out with this blue, which represent the past, I would say, and this red, which represent the future. Now, if we choose one event in 2014 with here a little more than 300 millimeters in one day, what you can say here is that the probability now to have this event is 3 times higher in 2014 than it used to be in 1950. Okay, this is the only thing we can say. We can say, yes, climate change is responsible for that, but only the probability that this event occurs is 3 times higher than in the absence of climate change. Okay, and so I will skip, I would say, because this is, no, I will not skip, because no, you showed the average precipitation. So this is the trend of heavy precipitation, extreme precipitation in the end of this century from 3 models, and you had an introduction on the models and their, of course, the weakness and strengths. And this is also for fall, winter, spring, and summer. And the point that I want to address here is in percent is that all models give more or less a trend here in, it's more or less green everywhere. There is more uncertainty during spring and summer, but at least during winter, all models give some green trend, so an increase in heavy precipitation in the future. So back, and so this will also illustrate what Piero said. However, regarding precipitation, there is, so this is one IPCC report on extreme events. There is limited to medium evidence available to assess climate-driven upset changes in the magnitude and frequency of floods at regional scale. So even though the Mediterranean area is kind of favorable region to look at them, it is still, at the global scale, it's still limited to medium evidence of the impact of climate change on floods. It's totally the reverse with droughts and heat waves, and which have the most, let's say, long-term economic cost and ecosystem stress. Here I show well, many examples, so reduced water supplies for public industry, power generation, reduced agricultural, forestry, fisheries productivity, increased fire risk, damage wildlife habitat, and increased livestock mortality rate. So what I want to stress here, for example, these paper showed the population and the water shortage from the 1800 to, let's say, nowadays. And you see that, of course, with time, you will appear, so the western coast of America, especially California, which is quite often subject to water shortage, but you see that clearly the Mediterranean region is the hotspot of water shortage in this region. So this is, as Piero said, due to not only climate change, of course, but to the usage human being make of the land, okay, going from agriculture, how they take the water reserve. So it's not only climate change, of course, in this, but still. And this is, once again, okay, Piero showed with a map the population growth. So here, this is the total in the Mediterranean. Here it's the northern shore of the Mediterranean. Here it's on the southern and east shore of the Mediterranean. This puts some strain, some pressure, some stress on the water resources. We have also, over the whole Mediterranean, and especially on the south, a change in agricultural demand and diets. Also, we're less responsible. We feel less responsible of the water we use because we're in a connected world. And do you know what it is? Please raise your hand if you have any idea. Yes. Yes, it's a golf. Okay, it's an 18-hole golf. Here it's in the Arabic Peninsula. And so unsustainable water use. And in terms of climate change, we see that the potential for drought at the end of this century is the highest nearly in the Mediterranean. Okay, so for example, we had a major one in 2003, so, which combined, of course, a heat wave, so major temperature anomalies with a lack of water in the soil, lack of water in the rivers, and which increased significantly the risk of fires. And it was the worst in 23 years for forest fires. And for example, in Portugal, nearly 6% of the forest area was lost, with a large impact on productivity, so impact on production in agriculture and forestry, with the financial impact here. Of course, it increased mortality significantly. The one that I like most is this one. This is the temperature in gray, and this is the number in, of deaths. And if you're not convinced that there is a relationship between the two, I can't do anything for you. So, back again, so we have different data sets with Piero. So I will show. So. Basically, so this is it's across the Mediterranean, so it's a Mediterranean average. I don't remember the zero, which period was taken to make the average, I would say. But this is the trend from 1900 to 2010 in precipitation across the Mediterranean from, so there's a combination of several data sets. And what we see is that after typically the 70s, we enter a period of, let's say, deficit of annual precipitation. Of course, you see that from year to year, this can evolve significantly. If we put a model for a land surface model and we apply it to this type of observations, then you see that we have a declining soil moisture in the Mediterranean. So this is the soil moisture index, which falls down also after the 70s, and with the area of droughts, which increases also significantly after the 70s. And as Piero showed, there is a clear divide between Northern Europe and Southern Europe in terms of trend in precipitation, so it's yearly average precipitation. Here it's not a gridded product that, as Piero showed, it's only on some stations here, but you see that besides the individual spots that Southern Europe and the Mediterranean area will experience also a decrease in annual precipitation. So, I will summarize. Oh, but it's not fair. I can have a long conclusion? No. Over lunch. Okay. No, this is the European summer temperature. So the average is 0 here. And what is really interesting here is these are the heat waves. And you see that the largest heat wave, so here it's a 1 degree Celsius anomaly. Here we are in the, let's say, a very, very rare, very events. And you see that all the most extreme, no, it's here it's normalized, sorry. It's not degrees here. The most extreme heat waves occurred in the last 15 years. Okay, so there is no doubt that climate change is responsible for that. And this is, I think, my last but one slide. Okay, what is interesting here, of course, this is on this sketch here, it's as a function of time, so it's 2010 and 2090. It's some indices showing how, let's say, aridity will increase, and basically what you have to show, but that was shown already by Piero, dryness should increase in all models of the last IPCC report. And the last slide, which I feel is interesting, is this divide between north and south. So there are two ways that you can increase the extremes, okay? You can either, warm, the average, the mean temperature increases, and so the distribution follows, or you can enlarge the distribution. Okay, and this is the main difference between north and south. Sorry. In the Mediterranean, basically, the increase of extreme is due to a temperature change. So there is a shift, really, of the distribution with the future. All the distribution, okay, moves to a warmer temperature. Whereas in Northern Europe, the increase of extreme temperature is mainly due to a change in temperature variability, not so much to a temperature, an average temperature increase. So there is a medium confidence then since the 50s, some regions have experienced trends towards more intense and longer droughts, and Southern Europe and West Africa are put, are highlighted. And there is a medium confidence that anthropogenic influence has contributed to some changes in the drought patterns. And this is my last slide. I wanted just to, so I put, this is in French, so you'll see if we raise the temperature very slowly, the frog does not notice anything. And this is our main problem. So when do we start doing something? Okay, thank you with that.